Have you ever wondered what it really takes to build an online service? Not just, a simple website, but something people rely on day in, day out. Something truly solid.
Hmm.
Today, we're kind of decoding the secrets, transforming a basic web app into what they call production-ready software as a service, or SaaS. It's like finding the blueprint for successful online stuff.
That's a great way to put it. Yeah. Building SaaS, it isn't just about the software itself, the code.
Yeah,
It's really about delivering a service.
right.
And there's this kind of unspoken contract, you could say, with the user.
An unspoken contract, okay.
Yeah, that it'll be there when they need it, it'll work well, it'll be secure, and it'll just meet their needs consistently.
Yeah.
That contract, it underpins everything.
Okay, I like that. And our mission today in this deep dive is basically to pull out the really key nuggets from big sources like building modern SaaS and the production-ready SaaS blueprint.
Yeah, cut through the noise.
Exactly. Give you the shortcut to getting, properly informed, find those surprising bits, the essential stuff.
So that unspoken contract you mentioned, always on, performs well, secure, that sounds like a lot of pressure. What really separates a production-ready SaaS from just, I don't know, a regular web app? What's actually in that contract?
Well, it really boils down to four key principles. These make the difference between, say, a side project and a professional service. First up, scalability.
Okay.
And this isn't just handling a few more people, it's the app's core ability to efficiently handle growth, more users, more tenants, more data, thinking almost like near infinite growth.
Wow.
And that usually means focusing on horizontal scaling, so adding more standard servers, spreading the load.
Rather than just making one server massive.
Exactly. Instead of just trying to, beef up one single machine vertical scaling, it's like adding more rooms to your house, not trying to make one room infinitely bigger.
Yeah.
Much more cost-effective and flexible long-term. Scaling out, not up.
Yeah. Okay, that makes total sense for handling growth spurts and keeping costs down.
Precisely. Second, you've got high availability and reliability. This is all about ensuring people can always access the service and that it performs consistently, even when, inevitably, some component fails.
Things do break.
They do. So you need redundancy built in, no single point of failure. Often that means running across multiple data centers, right?
Yeah.
With systems ready to take over, instantly failover. And you need to spot and fix faults super fast.
Because downtime.
Downtime in SaaS, it's not just annoying. It's genuinely a breach of that trust we talked about.
Yeah.
And it's a direct hit to revenue. Think about, your go-to work app suddenly dying right before a deadline. It's not just lost time, it chips away at your confidence in that service. Rebuilding that trust takes ages.
That's a really powerful way to frame it. Erosion of confidence.
Yeah, that changes how you think about an outage.
It absolutely should. The third principle, security is a foundation. This is huge, especially for multi-tenant platforms where you've got lots of different customers using the same underlying system.
Right, sharing resources.
Security can't be an afterthought here. It's non-negotiable from day one.
Yeah.
You need things like data encryption, both when it's stored and when it's moving around. Strong access control, who can do what. Strict data isolation between tenants, that's critical. And constantly monitoring and auditing what's happening.
Makes sense.
And here's maybe a surprising stat. Apparently, over 66% of users have actually deleted apps because of privacy concerns.
66%? Wow, that's huge.
It is. It shows it's not just about protecting data technically. It's about fundamentally earning and keeping that user trust.
Yeah, it's not just a checkbox. It's core to the user experience.
Totally. And finally, number 4, cost effectiveness. How you design the whole thing, your architecture, it has to lead to a financially sustainable operation.
Gotta make money, or at least not lose it hand over fist.
Right. Your infrastructure costs need to align with how much it's actually being used and the revenue is generating. This often pushes people towards cloud services, especially the pay-as-you-go or serverless options.
Yeah.
Because they directly tie your spending to actual demand. You avoid those huge upfront costs or paying for servers sitting idle, like in the old data center days.
What's really striking is how intertwined these all are, isn't it? Like, you go for multi-tenancy to be cost-effective, but that immediately forces you into needing top-notch security for data isolation.
Yeah.
And then having all those tenants together means you absolutely need that high scalability to handle the combined load. It's like a web. Everything affects everything else.
The balancing act, definitely. Every choice has knock-on effects.
Okay, so we've got these foundational pillars: scalability, availability, security, cost. Great principles. But how do we actually build systems that live up to them? What's the modern architectural thinking here? The blueprint, if you like.
Well, there's been a pretty big shift away from what we call monolithic applications.
the monolith,
Right.
the big single chunk of code.
Exactly. The traditional approach where everything, user interface, business logic, data access, it's all bundled together in one large code base,
Yeah.
deployed as a single unit. And these can become, well, serious liabilities as the application grows.
How so? What are the main pain points?
Development just slows right down. Because any change, even a tiny one in a small corner, means you have to test and redeploy the entire thing.
Both. Yeah.
And the risk is way higher. A bug in one minor feature could potentially crash the whole application for everyone.
I can definitely picture the late nights and stress involved there. One slip up takes the whole service offline.
Precisely.
Mm.
And that's why microservices emerged as such a powerful alternative pattern.
Yeah.
The idea here is to structure your application as a collection of small, independent, loosely coupled services.
Okay, so breaking it down.
Yeah, each service is responsible for just one specific business capability. Think like user authentication is one service, the billing engine is another, maybe product search is a third. They're all separate autonomous units that communicate with each other, usually over a network.
And what's the real insight there? I mean, beyond just being smaller pieces, how does that fundamentally change things for building size?
Well, beyond just the modularity, it changes how teams think about failure and speed. Instead of this constant fear that one mistake brings everything crashing down, you design for resilience. You expect parts to fail sometimes, but you build it so the core service can carry on gracefully. But the big wins are really agility. Small, focused teams can work on their individual services independently. They can develop, test, deploy their service without coordinating massive releases with everyone else. That means much faster feature delivery.
Faster time to market. Nice.
Yeah. Definitely. Then there's technological flexibility, sometimes called polyglot programming. Different teams can choose the best programming language or database for their specific services needs. You're not locked into one stack for the whole system.
Okay, interesting. Best tool for the job, for each job.
Exactly. Then fault isolation. If one service has a problem or crashes, it doesn't necessarily take down the entire application. The others can often continue running.
So damage control limits the blast radius.
Right. And finally, granular scalability. This is huge. You can scale up just the services that are under heavy load, independently of the others. If your user authentication service is getting hammered, you scale that one up, but maybe the reporting service is fine. Much more efficient use of resources than scaling the whole monolith.
That sounds like a really fundamental shift. Okay, but then there's this other buzzword, serverless. When we talk about serverless, it doesn't mean servers just disappear. It's more about who manages them.
Precisely. Yeah, serverless can be a bit of a misnomer. Servers definitely still exist. But the key difference is that developers don't have to provision, manage, patch, or scale them.
The cloud provider does all that heavy lifting.
Exactly. AWS, Google Cloud, Azure, they handle all the underlying infrastructure management. It abstracts away a ton of operational complexity. Developers can just focus purely on writing their application code, their business logic.
But it's not magic, right? I hear things about, like, new challenges.
Oh, for sure. It introduces different paradigms you need to master. Things like managing application state differently or dealing with cold starts, the slight delay when a function hasn't been used recently. You have to architect around those for production readiness.
Ah, okay.
Yeah.
So you trade one set of problems for another, potentially. But you're focusing on your code. The cloud handles the server headaches.
Got it.
And the combination serverless with microservices. Yeah, that's where things get really powerful.
It really is. It's a fantastic pairing for modern SaaS. When you build your microservices using serverless functions, say AWS Lambda or Azure functions, you get some major advantages.
Like what?
First, basically zero infrastructure management from your side. The cloud provider handles it. Second, automatic and incredibly fine-grained scaling. Your functions can scale from literally 0 requests up to thousands per second, almost instantly, and back down again. The platform manages that scaling automatically based on demand.
Wow, so it just matches the load perfectly.
Pretty much. And crucially, the cost model. It's typically pure pay-as-you-go, or even pay-per-invocation. You only pay for the compute time your code is actually running, often measured down to the millisecond. If nobody's using a feature, you're often paying nothing for it to sit there.
That sounds incredibly efficient.
It is. So serverless microservices. It's a powerful, modern, and when done right, very production-ready approach for building SaaS today.
Okay, this is where, for me, it gets really interesting and maybe a bit scary. How on earth do you serve hundreds, maybe thousands of different customers, different companies from the exact same system, but keep all their private data totally separate and secure? This multi-tenancy puzzle sound like a potential nightmare if you mess it up.
It absolutely can be. Yeah, multi-tenancy is fundamental to the SaaS business model, right? It gives you those economies of scale. You share the infrastructure, the application logic, the operational costs across all your customers. That's how you make it affordable.
Right, one system, many tenants.
But the flip side is that challenge. Securely isolating tenant A's data from tenant B's data. A breach here, where one customer sees another's information. That's potentially an extinction level event for a SaaS company.
Existential threat. Yeah, okay. So how have people traditionally tackled this? What are the database patterns?
Historically, there have been sort of three main approaches at the database level, each with pretty significant trade-offs.
Okay, lay them out for us. What are the options and what are the headaches?
All right. Option one is database per tenant, sometimes called the silo model.
Okay.
Each customer, each tenant, gets their own completely separate, dedicated database instance, physically isolated.
Ah, okay. Sounds super secure.
It offers the maximum possible data isolation, yes, and it can sometimes be easier for certain compliance requirements like GDPR or IPO because the data is physically separate. But
There's always a but.
the operational complexity and the cost are the highest. Imagine having to manage, backup, update, and monitor hundreds or even thousands of individual databases. It's
Yeah.
a lot.
A management nightmare.
And it's really difficult to scale efficiently if you have a large number of tenants. So this model is usually only practical for maybe a small number of very high-value enterprise clients who might specifically require or even pay extra for that level of physical isolation.
Gotcha. Great security, but operationally painful and expensive for lots of customers. What's next?
Option two is schema per tenant. Here, all the tenants share the same database server or instance, but each tenant gets their own separate set of tables within that database, organized into a schema.
Okay, so sharing the server but separate table sets inside. A middle ground.
It tries to be, but honestly, it often ends up kind of combining the drawbacks without getting the full benefits of either extreme. You still have significant complexity, especially around migrating or updating database schemas across all tenants.
Ah, yeah. Changing hundreds of schemas sounds rough.
And you can still suffer from noisy neighbor problems, where one really active tenant uses up resources on the shared database server and negatively impacts the performance for other tenants. Many experts generally advise against this model these days.
So maybe not the best of both worlds after all. Okay, what's the third traditional way?
The third one is the shared database, shared schema model, also called the pool model.
Pool. Like everyone swimming in the same pool.
Kind of, yeah. Here, all tenants share the exact same database instance and the exact same tables. Data for tenant A and tenant B sits side by side in the same customer table, for example.
Whoa. How do you keep them separate then?
Logically, you add a special column, usually called tenanted, to pretty much every table that contains tenant-specific data. Then every single database query your application makes has to include a filter, like where tenanted current customer, to make sure it only retrieves or modifies data for the correct tenant.
Okay, so the application code is responsible for adding that filter every single time.
Every single time. Now, the upside here is huge. It's by far the lowest operational complexity you're managing just one database. It's the most cost-effective, and it's the easiest to scale in terms of adding new tenants.
But GT.
Another but. And I think I know where this is going.
Historically, this model carried the highest inherent risk of data leakage. If a developer, just once, forgot to add that tenanted filter to a query, or got the logic wrong.
Boom. Data breach. One customer sees another's data. Exactly. And I can tell you from experience, years ago working on systems like this, that fear, that one missed where clause in some complex report keeping you up at night, it was genuinely terrifying.
So cheap and scalable, but constantly walking a tightrope over a data privacy disaster. That does sound stressful, but I get the feeling there's a better way now, a modern solution that changes this calculus.
Absolutely. There is. And it's a real game changer for multi-tenancy. It's called row-level security, or RLS.
Row-level security, RLS. Oh.
RLS basically moves that critical tenant filtering logic out of the application code and into the database itself.
Into the database. How does that work?
You define a security policy directly on a database table. This policy essentially tells the database, whenever any query touches this table, automatically apply this extra filtering rule based on the currently authenticated user's tenant ID. So the database itself enforces the where tenanted equals current tenant logic.
Oh, wow. So the database handles it automatically, transparently.
Pretty much. The application code can often just query the table normally, and the database ensures behind the scenes that the user running the query only ever sees data belonging to their own tenant. The policy is enforced right at the data layer.
That sounds like a massive relief. Developers don't have to meticulously remember the tenanted filter everywhere. The database guarantees it.
Exactly. It provides really strong, transparent, and difficult to bypass data isolation.
But with the operational simplicity and the cost-effectiveness of that shared pool model.
Precisely. That's why RLS is widely considered the superior choice for most modern SaaS applications today. It gives you the best of both worlds, security-wise and operationally.
Okay, that's a fantastic solution to a really thorny problem. But if RLS is so good, why wasn't it always the default? Were there historical limitations, or are there still edge cases where it might not fit?
That's a fair question. Historically, yeah, RLS features weren't as mature or universally available across all database systems as they are now. Postgres, SQL Server, others have really robust implementations today, but that wasn't always the case. So many older systems had to rely on application-level filtering.
Okay, tooling maturity.
Right. And also, while RLS is brilliant for data isolation, it's not a magic wand for all security. You still absolutely need strong authentication, proving who the user is, and authorization, what they're allowed to do in your application layer. RLS focuses specifically on ensuring they only see their own data within the tables they are allowed to access.
Got it. It's one critical piece of the security puzzle, not the whole puzzle.
Exactly. And maybe, just maybe, for that tiny fraction of super high security, heavily regulated enterprise clients, the old database per tenant silo might still be insisted upon, perhaps even just for the sort of psychological comfort of total physical separation. But honestly, for probably 99% of modern SaaS use cases, RLS hits the sweet spot, balancing security, cost, and operational ease beautifully.
Okay, so we've architected for scale. We figured out secure multi-tenancy with RLS. Now, how do we actually build the software components themselves? How do we bake quality in from the very first line of code? It's easy to say, write good code, but what's the actual discipline that helps achieve that consistently?
Yeah, that's where a practice called test-driven development, or TDD, comes into play. And it's really important to understand that TDD isn't just about testing, like running checks after you've written the code. It's fundamentally a design technique.
A design technique? How so? You're writing tests first.
Exactly. You flip the usual process. Before you write any production code for a new feature or fix, you first write an automated test that describes what that code should do, and which will initially fail because the code doesn't exist yet.
Okay, so you're not just coding and then figuring out how to test it later. The test actually guides how you shape the code. That feels like a big mental shift from how a lot of people learn to program.
It really is.
Yeah.
And it forces a much more deliberate, focused approach to design. TDD follows this very specific discipline rhythm called the red-green refactor cycle.
Red-green refactor.
First, red. You write a small, specific, automated test for a tiny piece of functionality that you haven't implemented yet. This test acts like a precise executable specification. It defines exactly what success looks like for that piece of code, and crucially, when you run it, it must fail. Go red, because the actual code isn't there.
Right, the test fails, and that's actually good news at this stage. It means you've clearly defined the target.
Exactly. Step 2, green. Now, you write the absolute minimum amount of production code necessary to make that specific failing test pass. Go green. The key phrase here is minimum amount. You resist the urge to add extra features or gold-plate it. Just do enough to satisfy that one test. This prevents over-engineering.
Just enough to pass.
Okay. And finally, step 3, refactor. Now that you have a passing test proving the basic functionality works, and you have that safety net, you can confidently look at the code you just wrote, and potentially other related code, and improve its internal structure. You clean it up, remove any duplication, make it more readable, maybe optimize it slightly, all while continuously running the tests to ensure you haven't broken anything.
So the refactoring happens after it works, with the tests acting like guardrails.
Precisely. And this refactoring step is honestly where the true design benefits of PDD are realized. It's this constant cycle of improvement done safely that prevents technical debt, that cruft and complexity that builds up over time from accumulating.
So the tests aren't just bug catchers. They actively force you to think about design up front, they keep your code minimal and clean, and they give you that safety net to make changes later without fear. That really is a fundamentally different approach to software development.
It absolutely is. Adopting a TDD mindset generally leads to cleaner, more modular designs because you're forced to think about how to make code testable, which usually means making it decoupled. It results in higher code quality with fewer bugs. You get that comprehensive safety net for confident refactoring down the line. Debugging often becomes faster because when a test fails, you know the problem is likely in the small amount of code you just changed. And the tests themselves end up serving as excellent, up-to-date, living documentation of how the code is supposed to behave.
Living documentation, I like that. Better than comments that get out of sync.
For sure. And just to circle back to multi-tenancy, when you're building a SaaS with something like RLS, it's absolutely critical to have specific integration tests within your TDD practice that explicitly verify the tenant isolation. You need tests that set up data for tenant A and tenant B, then log in as tenant A, and prove programmatically that they can only see tenant A's data and absolutely cannot see tenant B's. That's how you validate your RLS implementation is working correctly under real conditions.
Right. Testing that core promise of the sauce directly. Makes sense. Okay, so TDD gives us confidence in the code itself. But what about the complex cloud infrastructure that this sauce application lives on? How do we manage all those servers, databases, networks, load balancers reliably and repeatably? Surely we're not just clicking around in the AWS or Azure console every time we need a new environment or an update.
Hopefully not. No, that's where infrastructure as code, or IAC, comes in. It's exactly what it sounds like, the practice of managing and provisioning all your computing infrastructure. The networks, VMs, serverless functions, databases, everything using machine-readable definition files. Code.
So you write code to define and build your infrastructure. That sounds kind of meta, but also incredibly powerful for consistency, right?
It is extremely powerful. You essentially treat your infrastructure with the same disciplines you use for your application code. Version control, code reviews, automated testing.
Okay, so what are the big benefits?
The biggest is probably achieving predictable, repeatable environments. Your IAC code becomes the single source of truth, defining exactly what your infrastructure should look like. Run the code, get the environment, run it again, get the same environment. No more manual configuration drift or it works on my machine problems for infrastructure.
Nice. How does it work in practice?
Most modern IAC tools, and Terraform is a very popular example, use the declarative approach.
Declarative.
Yeah, instead of writing a script with step-by-step commands like create server, configure network, install software that's imperative, you declare the desired end state. You write code that says, I need a network with these subnets, a database server with this configuration, and 3 web servers behind a load balancer.
Oh.
You define what you want, and the IAC tool figures out how to make the current reality match that desired state.
Ah, okay. You describe the target, it handles the steps. That sounds much less error-prone than scripting every command.
It generally is. And related to that is a key property called idempotency.
Idempotency. Right. Can you unpack that a bit? Why is that so important for IAC? Does it stop you accidentally creating duplicate stuff?
That's exactly it. Idempotency means that applying the same IAC configuration multiple times will always result in the same end state, without causing errors or unintended side effects after the first successful application. So if you run your Terraform code to create a database, it creates it. If you run the exact same code again against the same environment.
It doesn't try to create a second database.
Correct. It looks at the current state, sees the database matching the desired configuration already exists, and does nothing. Or, if maybe a setting had drifted manually, it would correct just that setting to match the code. It makes applying changes safe and predictable, which is absolutely vital for automation. You don't want your automation accidentally creating duplicate resources or breaking things on reruns.
That makes perfect sense. Safe reruns are key for automation.
And crucially, these IAC definition files your Terraform code. For instance, they live in version control, like Git, right alongside your application code.
Ah, so you get the whole history.
Exactly. You get a full, immutable audit trail of every infrastructure change. You can collaborate on infrastructure changes using familiar workflows like pull requests and code reviews. And if a change causes problems, rolling back is often as simple as reverting to a previous version of the code and reapplying it.
That's fascinating. We're not just clicking buttons. We're writing version-controlled, reviewable code that reliably builds our entire environment every single time. Why is Terraform often the go-to tool for this?
Terraform has become incredibly popular for a few key reasons. First, it's cloud agnostic. It has providers for AWS, Azure, Google Cloud, Kubernetes, even on-prem stuff, hundreds of services. This helps avoid vendor lock-in and makes multi-cloud or hybrid cloud strategies feasible.
So one tool to rule them all, potentially.
Potentially, yeah. Second, it uses its own purpose-built declarative configuration language called HCL, HashiCorp Configuration Language. It's designed specifically for defining infrastructure and is generally considered pretty human-readable. Third, it has strong support for modularity. You can create reusable infrastructure components, like a standard way to set up a VPC network or deploy a database, and reuse that code across different projects or environments.
Reusability, nice. Saves effort.
And finally, it just has a really mature ecosystem. Huge community support, lots of pre-built modules available, widely adopted, making it kind of the industry standard for declarative IAC right now.
Okay, and just like we talked about TDD for application code, you can apply that thinking to infrastructure code too. Test-driven infrastructure.
Absolutely you can. And you should. This is test-driven infrastructure, or TDI.
Yeah.
It's about extending those TDD principles to your Terraform code, or whatever IAC tool you're using.
How does that work? You can't really unit test a cloud resource, can you?
Not exactly unit tests, but more like integration or end-to-end tests for infrastructure. You use tools. TerraTest is a popular one in the Terraform world to write automated tests that actually perform a sequence like that. 1. Run your Terraform code to provision real infrastructure resources in a temporary isolated environment, like a dedicated AWS account. 2. Validate that the infrastructure was created correctly. Check if networking rules are right, if services are accessible, if security settings are applied as expected. 3. Then, critically, run Terraform again to destroy all the resources created for the test, cleaning up after itself to avoid costs. Wow, so you're actually spinning up and tearing down real cloud stuff in your tests. Yes, it's incredibly powerful because it catches errors that you'd never find just by looking at the code. Functional bugs, security misconfigurations, maybe even unexpected cost implications in how resources interact. You find these problems before your infrastructure code ever gets applied to a staging or production environment.
Catching infra bugs before they hit production. That sounds incredibly valuable. Okay, this is amazing. We've got our scalable, secure architecture, maybe serverless microservices. We've got our application code built with the confidence of TDD. We've got our infrastructure defined reliably with ISC, maybe even with TDI. Now, the grand unification. How do we tie all these pieces together? How do we actually deliver changes, new features, bug fixes, infrastructure updates safely, automatically, and repeatedly into production?
Right, this is where it all comes together in the CI/CD pipeline, often orchestrated using principles from an operational model called GitOps.
GitOps. Okay, I've heard that term. What's the core idea?
The absolute core principle of GitOps is using Git as the single source of truth and the central control mechanism for everything related to deploying and managing your application and its infrastructure.
Single source of truth. So if it's not in Git, it doesn't count?
Pretty much. All desired state application code, infrastructure definitions, like your Terraform files, configuration settings, even the definition of the CI/CD pipeline itself lives in Git repositories. And crucially, all changes are initiated, reviewed, approved, and merged via standard Git workflows, primarily pull requests or merge requests.
No more manual sloshing into servers to deploy code or tweak configs.
Exactly. Manual changes are actively avoided. Git becomes the gatekeeper and the audit log for every change that happens in your environments.
So Git isn't just for code anymore. It's the control plane for operations. How does this plug into a CI/CD pipeline? Maybe walk us through an example, say, using GitHub Actions.
Okay, yeah, GitHub Actions is a great example. So first, remember the everything is code idea. Your application source code is in Git. Your automated tests, both unintegration tests for the app, maybe using PyTest, and your infrastructure tests like TerraTest are also in Git. Your Terraform code for IAC is in Git. And the YAML files that define the GitHub Actions workflows, the CI/CD pipeline steps, are also stored in the same Git repository.
Right, the pipeline itself is code, versioned alongside everything else. That's really powerful.
It is. So now a developer wants to make a change, maybe add a feature, they create a branch, write the code, write the tests, TDD, maybe update some Terraform if needed. Then they open a pull request, PR, in GitHub.
Okay, the standard developer workflow.
Right. But opening that PR is the trigger. It automatically kicks off the continuous integration CI phase defined in your GitHub Actions workflow. This usually involves jobs running in parallel. Yeah. One job might be test application. It checks out the code, builds it, runs all the unit integration tests, PyTest, etc. Another job might be test infrastructure. Yeah. It runs your TerraTest scripts to validate the Terraform changes proposed in the PR, during that spin-up validated destroy cycle we talked about.
So automated checks fire immediately on the PR.
Yes, and GitHub can be configured so that the PR cannot be merged into the main branch until all of these automated check jobs pass successfully. It's a critical quality gate.
So quality is enforced before the code even lands in the main development line. That prevents so many downstream problems, doesn't it?
Absolutely. It catches issues early and often. Once the PR passes all checks and gets reviewed and approved by teammates, it's merged into the main branch.
Okay, merge happens. What next?
The merge into main typically triggers the next stage, an automated build and artifact creation job. This takes the validated code, builds it into immutable deployment artifacts. Very often, these are Docker container images. These images are tagged, perhaps with a git commit hash, so you have perfect traceability back to the exact code version. They get pushed to a container registry.
Immutable artifact. So the thing you deploy is fixed, built once.
Exactly. You build it once, test it, and then deploy that exact same artifact through your environments. Then comes the continuous deployment CD phase. This is also defined in your GitHub Actions workflow.
Automating the actual release.
Right. Deployments to a staging or testing environment are often fully automated right after the build. The pipeline might use Terraform via Terraform workspaces to manage different environments like staging versus prod, to apply infrastructure changes, and then deploy the new Docker image to that staging environment. This gives the team rapid feedback on how the changes behave in a realistic setting.
Quick feedback loop. Good. What about production? Is that just fully automatic too? Click merge and it goes live.
It can be, but for many critical SaaS applications, production deployments are typically gated by a manual approval step. GitHub Actions environments, for example, allow you to require a specific person or team to manually approve the deployment job before it proceeds to production.
Ah, okay. So there's a human safety check, a final go-no-go decision before it hits real users.
Exactly. It's a crucial control point. The process leading up to it is fully automated and validated, but that final step often involves human judgment. Once approved, the workflow then runs the deployment steps, again, likely using Terraform and container orchestration commands, to roll out the change to the production environment.
So just to recap for everyone listening, what does this whole GitOps CI/CD flow really mean? What's the big takeaway?
It means that every single change, whether it's a tiny one-line bug fix or a massive new feature involving code and infrastructure updates, goes through the exact same rigorously tested, automated, peer-reviewed, and fully auditable process from the developer's keyboard all the way to production.
That sounds like, well, genuine confidence in your deployment process.
It really is. The benefits are huge. Full auditability Git history tells you who changed what, when, why, and whether it passed tests. Enhanced collaboration and review via pull requests. Increased reliability and consistency because automation eliminates manual errors. And improved security by having standardized auditable paths for all changes and potentially restricting direct access to production environments. It transforms releases from high-stress, risky events into routine, predictable operations.
Okay, the code is built with TDD, the infrastructure is managed with ISC, the deployment is automated via GitOps CI/CD. The change is now live in production. Is the job done? Or is there more to this production-ready journey even after shipping?
Oh, definitely not done. Deployment is really just the start of a whole new ongoing phase. Being truly production-ready means you're constantly monitoring, optimizing, and learning from the system running live. This is where production observability becomes critical.
Observability. So understanding what's happening inside the live system, how do you keep that unspoken contract with the user intact once it's out there?
You need robust logging and monitoring. That means first, centralized logging. All your application logs, system logs, function logs, everything needs to be collected in one place. Services like AWS CloudWatch logs or Datadog are common for this. It makes debugging issues so much easier than trying to hunt logs across dozens of servers or functions.
One place to look for clues. Makes sense.
And you need to be tracking key performance and health metrics. Things like, for serverless functions, the number of invocations, error rates, execution duration. For databases, connection counts, query latency, you need dashboards to visualize these. But crucially, you need alarms. Setting up things like CloudWatch alarms to proactively notify your team via Slack, PagerDuty, whatever, if critical metrics cross dangerous thresholds, like if the error rate suddenly spikes.
So you're not just waiting for customers to complain that something's broken, the system tells you first.
Exactly. Proactive alerting is key to minimizing impact. And using structured logging messages in the consistent format like JSON rather than just plain text makes querying and analyzing those logs much, much more powerful later on.
Okay, monitoring for health and errors. What about costs? Does that just take care of itself once it's live?
Definitely not. Cost management is an ongoing discipline, especially with cloud pay-as-you-go models. You need to regularly analyze your spending patterns. Tools like AWS Cost Explorer are essential for understanding where the money is going. You should set budgets and configure billing alerts to notify you if costs start trending higher than expected. Keeping the service financially viable is part of being production ready.
Right, gotta keep an eye on the bills. And beyond just keeping the lights on and costs down, are there other ongoing improvement areas?
Always. You should be thinking about advanced security. Maybe implementing a web application firewall, EVF, for extra protection against common web attacks. Continuously reviewing and tightening permissions using the principle of least privilege across all your cloud resources. Integrating static analysis security testing, SaaS and dynamic analysis SaaS tools directly into your CI/CD pipeline to catch vulnerabilities automatically.
So security isn't a one-time setup, it's an ongoing hardening process.
Precisely. Then there's cost optimization. Beyond just monitoring, actively looking for ways to tune things. Maybe exploring advanced features like Lambda provision concurrency to reduce cold starts for critical, latency-sensitive functions, balancing cost and performance.
Fine-tuning the engine.
Yep. And evolving your advanced CI/CD patterns. As you mature, you might implement more sophisticated release strategies like blue-green deployments, running two identical production environments and switching traffic, or canary releases, gradually rolling out a change to a small subset of users first to further minimize the risk of deployments impacting users.
Even safer ways to release changes.
Right. And finally, always be exploring alternative tooling. The tech landscape changes fast. While your current stack, say Terraform, GitHub Actions, AWS Lambda, might be great, keeping an eye on alternatives like Pulumi for IAC, which uses general-purpose languages like Python or TypeScript, or other CI/CD platforms like GitLab CI or Circle CI, broadens your perspective and ensures you're aware of new possibilities or better fits for future needs.
It's really clear that the whole thing is a continuous loop, isn't it? The data you gather from monitoring and observability feeds right back into the next cycle of development, informing new features, bug fixes, performance optimizations, even architectural tweaks. It closes that DevOps loop:
Yeah,
build, ship, learn, iterate.
that's exactly it. Production readiness isn't a destination you arrive at. It's a state of continuous vigilance and improvement.
Wow. What an incredible journey we've taken, really mapping out this blueprint for production-ready SaaS. We went from those core principles, scalability, availability, security costs, through modern architectures like serverless microservices, dug into test-driven development, infrastructure as code, and finally that automated CI/CD pipeline, tying it all together with GitOps.
And I think the profound synergy between these practices is what really stands out, doesn't it?
Yeah.
TDD isn't just about code quality. It validates your architecture's promises, like proving RLS actually isolates tenant data. IAC doesn't just automate infrastructure. It enables these complex, scalable architectures like serverless microservices to even be manageable.
Yeah, absolutely. And the CI/CD pipeline isn't just automation, it's the engine that operationalizes it all. It runs the TDD checks, uses the IAC to build environments, and forces the GitOps flow. It really empowers teams to build these complex, scalable, reliable, secure products with a level of confidence that honestly was hard to imagine maybe 10 or 15 years ago.
Totally agree. It's a powerful combination of practices.
So here's a final thought to leave you with. If the whole point of building a production-ready SaaS is this cycle of continuous improvement, constantly adapting to a changing landscape, what might it look like if you applied that same mindset, that dedication to constant learning, feedback, and refinement to your own journey, whether that's in technology or really in any complex field you're passionate about? Understanding these practices, from designing for failure to automating everything you can, it gives you a more mature, quality-focused, maybe even more resilient way to approach building anything complex. It's really about building with confidence, isn't it? Every single time.